Hi kids, me again. Today we're going to review winds and we're going to continue with winds into something called the Coriolis effect, which is very cool because you and I are on a rotating planet. And when things spin, everything spins. So first we're going to review, then we're going to do some new material. You need a notebook to write some notes. You need page 14 of your reference table. You can get that ready. And let's begin. I'm going to turn the camera around so that we can review. Let's first remember that wind is caused by uneven heating. Those two words are going to be important. Uneven heating of Earth's surface. Why? Because the sun does not strike the Earth's surface evenly. Hits dead on at the equator, comes in at a much lower angle at the poles. That is why the equator is warm and the tropics. That is why the poles are cold. And that causes wind. How? Because temperature determines pressure. You will recall from the thing that we did, I don't know if you could see it in the background, we prepared this beautiful document. Remember this? We made this of how the winds change based on the temperature of the air. So if the air is cool, it is dense, it drops, exerting higher pressure, keeping moisture out. If the air is warm, it is expanded, and therefore it wants to kind of rise, and that allows moisture in. That makes for cloudier, rainier, wetter weather. And this beautiful cycle is called convection, and it happens in all fluids. Please remember that fluids are liquids and gases. Gases are fluids. They're not liquids, but they are fluids. And convection occurs in fluids. Okay? Critical understanding, winds blow from high to low pressure. Winds blow from high to low, but from cool to warm temperature. Every breeze is a cool breeze. Check out your air molecules diagram, which is the one I just showed you. Highs blow, lows suck. Good. This is just review. We talked about the temperature and pressure gradient. Where there's the biggest change in the shortest distance, you will have the fastest wind speed. And you will know that based on the spacing of isobars. If the isobars are close together, there is a faster wind speed. If the isobars are further apart, is a gentler wind speed. Please remember that high pressure is cool temperature. They will draw that with blue. Low pressure is warmer temperature. Remember, this is not cold and hot. These can just be a few degrees apart. This is the same day all over the United States. But maybe this was, I don't know, 50 degrees, and maybe this was 55 degrees. That is enough to change the pressure and change weather patterns. Here there's a rapid change in pressure in a short distance. These are isobars. You could tell by these numbers that this is measured in millibars. You know, 1008, 1004, 1000. This is a contour interval of 4 millibars. But because they're so close together, high wind speeds. Because they're so far apart, gentler wind speeds, slower wind speeds. Okay, that's just review. This, remember, is an anemometer, measures wind speed. Those little cups measures wind speed. This is a wind vane, and they tell the direction that the wind comes from. Please remember that winds are named after where they come from. This is just review, where they come from. I hope you remember that this one's fake because there's no tail. You need the tail. You need this part. That is how the wind kind of pushes the needle into the direction that the wind is blowing from. Again, a north wind is from the north. A south wind is from the south. Coming from the south, blowing elsewhere. Going from the north, blowing to the south, for example. Okay, north winds are cooler, south winds are warmer. And here is a combination of both. This is just review, and then we drew breezes. We drew this. We started with a sea breeze. If it is sunny out, there is a sea breeze, right? Because at the beach, during the day, the sand gets very hot. That heats the air above it. That creates a low pressure area where the warm air wants to rise. And over the ocean, over the sea is much cooler during the day. It makes the air drop. It's cool. That will exert higher pressure. Winds blow from high to low. Winds are named after where they come from. That's why this is a sea breeze. Remember, if it's sunny out, If it's during the day, if it's a beautiful summer afternoon, sea breeze. Sunny, sea breeze. And we also drew this last time. Not that. Sorry. This. Land breeze. Lunar land breeze. At night, now the temperature of the land is much cooler, so that's where the high pressure is. And now, since the water's been heating up all day, it's significantly warmer than it was earlier in the afternoon. So now the warm is here, the cool is there. That makes high pressure over the land, low pressure over the sea. Winds blow from high to low, and they're named after where they come from. This is a land breeze. Very good. That's kind of where we ended with the last lesson. I hope you understand it. Showed you some diagrams of it. And we got up to slide, I believe it was this one. Yeah, slide number 20. The numbers of the slides are over here. I didn't tell you that last time, but that's where they are. Today, we're going to do something new. I'm going to pause this for a moment. Kids, I'm going to try to teach you as though we're in school. I don't know if this is going to work. If you guys could like hit me up and actually tell me how this is working for you, let me know if this works for you. This is the best I can do from home. I'm really trying. Just let me know. Maybe send me a private email or send me something on my mind. Let me know if this is working for you, okay? But draw this with me. Here's the Earth. There she is. I hope you can see that all right. All right? Remember that winds blow from high to low pressure. If this is the equator, I hope you know what the temperature is like at the equator. We know that this is warm. And if the equator, and in fact, the Tropic of Cancer, the Tropic of Capricorn, if those are warm, do they exert higher or lower pressure if they are warm? Think about it. Warm air is expanded. That would be low pressure. So I want you to write warm and low over here. Low pressure. Warm temperature, low pressure. Think about where it is cool. Up here and down here in the Arctic and Antarctic Circle. This is where it is cool, right? Because the angle of the sun comes in at a much lower angle. If it is cool, that makes it high pressure. And high pressure wants to sink. Sink where? Sink towards the surface of the Earth. That is sinking. Sink towards the surface of the Earth because it's high pressure and it's condensed. Well, remember that winds blow from high to low. Winds blow from high to low pressure. And if the Earth stood still, this is what it would look like. All the wind would want to blow from the poles to the equator. And in fact, they do, because winds blow from high to low. Winds do blow from the poles to the equator, and they do blow generally in straight lines. The problem is, this is somewhat wrong. I want you to have drawn this, but then I want you to put a big X through it. And every year I get kids yelling at me right now, Miss Kay, why did you make us draw it if you want us to put an X through it? Put an X through it, but just an X. Don't scribble it out. I want you to still be able to see this. Here's why. This is what happens, except this is on a stationary Earth, and the Earth is not stationary. We're turning, we're rotating at 15 degrees per hour. And so, in fact, it does not go so simply like this. Let's draw another picture, shall we? Let's draw what really happens. And I want you to write the Coriolis effect on your notes. I'm going to attach a picture from my notes into your Google Classroom today, just so that you understand this a little bit better. Draw yourself another Earth. This time we're going to make it a little bit bigger. You know what? Let me make this so that it doesn't move around. Okay. And I want you to draw the equator. And I want you to label that this is, of course, the northern hemisphere. And you are going to label the bottom the southern hemisphere. In class right about now, I would grab a globe and I would grab a dry erase marker and I would actually draw on the globe what happens. In the last picture that we drew, the winds were blowing from the poles to the equator, and that is sort of what happens. However, the Coriolis effect is basically a spin. Because the Earth is turning, the winds, rather than blowing in straight lines, curve. And I want you to draw this. Go about halfway between the equator and the pole, and I want you to write the word clockwise right here. And I want you to draw some arrows curving to the right above the word clockwise. And then underneath, if you could follow this arrow's curve around almost into a circle, you can continue that arrow right here. Follow this curve around and then continue that arrow right here. Pretend you're making a circle and then continue that arrow right here. And in fact, winds circulate clockwise in the north and counterclockwise in the south. Down here, you can write counterclockwise. And so, curve it. Curve it. And notice that these arrows are sort of converging at the equator. They're coming together at the equator. And if you were to follow this arrow around into a circle, it would make another arrow here. If you could follow this circle, this arrow's curve around into an imaginary circle, it would create another arrow here. This one would create another arrow here. And that's what happens. So rather than going in straight lines like this from the poles to the equator, because the Earth is rotating counterclockwise, it puts a spin on the wind. And the wind circulates clockwise in the north, counterclockwise in the south. Clockwise in the north, counterclockwise in the south. I added a little bit of note right here. What that means is that winds will deflect. They're going to use the word deflect. What that means is that they curve to the right in the northern hemisphere, to the left in the southern hemisphere. To the right in the northern hemisphere, which is the same as saying clockwise. To the left in the southern hemisphere, which is the same as saying counterclockwise. Now, and a place in this lesson that normally confuses kids pretty much every year is looking at these arrows. These look like they're going to the right. These look like they're going to the left. They're really going in the same direction. Let me prove it to you. If you look at this arrow curving to the right, right? And then turn this upside down and look at these bottom arrows. These are also going to the right. This is going to the left, so are these. Let's go back. Right? This is going to the right. If I turn this upside down, this is also going to the right. It looks different because it's upside down, but they are really making circles. Clockwise in the north, counterclockwise in the south, clockwise to the right in the north, the way of the clock, counterclockwise to the left in the south, the opposite way of the clock. If you look at my slideshow right about now, starting at slide 21, 20, yeah. This is a picture of what I'm trying to describe, the effect of Coriolis force. On a non-rotating Earth, winds will blow from the North Pole in straight lines down towards the equator. Remember that this horizontal line is the equator. These numbers on here, I hope you recognize based on the numbers that they are longitude. 15, 30, 45, 60 to the west, 15, 30, 45, 60 to the right. But they're just showing you the top half of the globe. In the northern hemisphere, winds will deflect to the right. And so that's what this is. Over here, this is on a non-rotating Earth. Straight line from the pole to the equator. This is just an aerial view looking down on the North Pole, straight line from the pole to the equator. But this is wrong because the Earth is not standing still. It is rotating. So now, on an Earth rotating 15 degrees per hour, that wind, although it's trying to blow in a straight line, because that Earth is turning, there's a little arrow right here. I wonder if you could see. You'll be able to see it if you open it yourself, the slideshow that is, yourself. There's a little arrow right here showing the counterclockwise rotation of the Earth that makes the winds deflect to the right. Now this looks like it's to the left. Remember, it's clockwise. Clockwise in the northern hemisphere. We are looking at the northern hemisphere only. This is the aerial view. This is the profile. This would be the aerial view. Looking down. The winds are trying to blow from the poles to the equator, and they are, but they spin out a little bit. Clockwise in the north, counterclockwise in the south. This picture was in the slideshow yesterday. This is looking down on the North Pole. You'll notice the color of the arrows are blue. That's because it is cold air. And so that air, when it drops, high pressure, cool and contracted, dense, weighs a lot, it drops. And when it hits the Earth's surface, from the atmosphere, when it hits the Earth's surface, it hits and it has no place to go but outward, and it spins outward and clockwise. You'll notice high pressure systems spin outward from the center, from where the air is dropping, outward, and there's a spin. This is called the Coriolis effect. Try saying that. Coriolis. Coriolis. That's how it's pronounced, Coriolis effect. And it spins the wind due to the Earth's rotation. In fact, this is proof that the Earth rotates at a rate of 15 degrees per hour. Now, kids, take a mental picture. This slide is very, very helpful. You have to know this image. Here's what I mean. You have to know, number one, that H and L stands for high pressure and low pressure. This is not about temperature right now. It's high pressure and low pressure. However, when they draw it, they should use blue for high pressure because blue is an indication of cool temperature, and red for L because red is an indication of warmer temperature. So again, this is not hot and cold. This is cooler and warmer. This could be 30 degrees. This could be 35 degrees. Still very cool, but this is still warmer than that. This could be 80 degrees. This could be 85 degrees, right? This is just Monday and Tuesday of any given season. But what I want you to notice is how the arrows spin. You have to know how these arrows spin. So when high pressure, when cool air hits Earth's surface, it drops and it has no place to go but out. When it spins out, it will curve to the right, clockwise, clockwise, clockwise. Do you see it? Now remember, highs blow. They blow outward and away from the high. Lows, however, suck. They pull that high pressure in. Winds blow from where it is strong and dropping to where it is light and fluffy, right? This wants to go up anyway. It's expanded, dude. It's all expanded. It's warm. It's happy. And so this cool air blows towards the low, and that pulls it in. Inward, you'll notice that these arrows are going inward and counterclockwise. Highs blow outward from where it drops and spins clockwise. Lows pull inward and spin counterclockwise. Counterclockwise. There is a way to remember this. And it sounds like you're trying to clear your throat or saying something dirty. You're not. Hock and lick. Hock, one C, and lick, two C's. You need to know this slide. Hock stands for high pressure, outward, and clockwise. High pressure, outward from the center. So this is an aerial view looking down on where this air is hitting the Earth's surface. When it hits Earth's surface, it has no place to go but outward, and it spins clockwise in the northern hemisphere. Clockwise. High, outward, clockwise. Hock. High, outward, clockwise. Hock. High, outward, clockwise. Say it 85 times. When you're done with that, lick. Two C's, lick. Low pressure, inward and counterclockwise. Low pressure, inward, counterclockwise. Lick. So now the winds blow from the high to the low, and the lows pull it in. But now it spins the opposite direction, counterclockwise. And I want you to look at these arrows. You have to know how to draw them. I'm going to show you how to draw them right now. Grab a slice. Make an H, put a circle around it. Make an L, put a circle around it. Go from the center and curve it to the right. Curve it to the right. Curve it to the right. This is clockwise. Curve it to the right. You see that? And then put your arrowhead on the top of each of these. Curve it to the right. Just start here, curve it to the right. If this doesn't look to the right for you, then turn it. Curve it to the right. If that doesn't look to the right, to the right. To the right, to the right. Curve it to the right. High, outward, clockwise. Hock. High, outward, clockwise. Hock. Something interesting with the lick it goes inward and counterclockwise, but I want to show you how easy it is to draw. If you know how to draw this, draw it the same way, to the right, to the right, to the right, to the right. And then the only thing you're changing is where you're placing the arrowhead. Place the arrowhead on the inside, the inside, the inside. Bring it towards the center. Lick, lick, low, inward, and counterclockwise. The arrow lines are drawn the same way. The only thing you're going to change is the arrowhead. And that is how you are always going to get this right. Curve it to the right. Hock, outward and clockwise, away from the high and clockwise. Spins outward. Lick, pulls inward and counterclockwise. But it's real easy to draw the same way. Look carefully at the way this is drawn. Look carefully at the way this is drawn. Outward and clockwise, inward and counterclockwise. Hock and lick. I know it sounds crazy. I don't care. It's the easiest way to remember it and get it right every time. All right? Here is a profile view. I love this profile view. We actually created this profile view in the drawing that we made together. I will show you now. At the top of this, high pressure, cool air, contracted, denser, all those things. It drops and spreads out, drops and spreads out. What you can't see on this profile view is that it goes outward and clockwise. Here, the high blows from the high over to the low, inward and counterclockwise. But what you can't see on this is the spin counterclockwise. But you can see the convection current. Highs blow, lows suck. Highs blow down and out, lows suck in and up. And that creates our weather patterns. That's what this is trying to show. Highs blow, it drops outward. Lows suck inward. Now you'll notice these clouds here. We haven't even gotten to cloud formation yet. But clouds form in the low pressure areas because that air rises, it makes it cool and contract, and creates clouds. We'll talk about the cloud formation later. But right now, just understand, happy, sunny, high, cool and dry. Lousy, cloudy, low, warmer, rain or snow. Sunny, high, cool and dry, cloudy, low, rain or snow. Sunny, high, cool and dry, cloudy, low, rain or snow. By repeating it, you learn it. That's called studying. Real easy way to study, okay? Now, see these drawings? You better know them. Lows, inward and counterclockwise. Highs, outward and clockwise. Winds around a low pressure system spiral inward and counterclockwise. Winds around high pressure systems spiral outward and clockwise. This is for the northern hemisphere. It's the opposite in the southern. But highs always outward, lows always inward. So here is a diagram of the variation between the northern and the southern hemisphere. The direction of circulation changes north or south of the equator, but highs are always outward, lows are always inward. So here's the equator. High outward clockwise, low inward counterclockwise. Here is south of the equator, the southern hemisphere. High and outward still, low and inward still. They just go in the other direction, okay? Here's another thing. A cyclone is the term for a storm, a bad storm, right? A hurricane, a cyclone, a monsoon. They're all kind of the same thing. They are very low pressure systems creating very bad weather. Cyclones. It's actually a roller coaster in Coney Island called Cyclone because it's like a bad storm, right? Whatever. Cyclones are storms. So the opposite of a cyclone, low pressure system, is an anti-cyclone. Opposite of a cyclone. These are beautiful weather, happy, high, cool, and dry. These are cyclones, storms, cloudy, lousy, low, warmer, rain, or snow, okay? Remember, why are the winds drawn in curved paths instead of straight lines? Why is this? Why are they curving? Why aren't they just blowing from high to low pressure, from poles to the equator, from cool to warm? Why? The answer is our beautiful Earth rotates. 15 degrees per hour, we're spinning. And so the air spins also. High outward clockwise, hock. Low inward counterclockwise, lick. Same diagram, same idea. This is the aerial looking down on that high. I know these words are very, very small, but when you open it, you'll be able to see it clearer. This says surface winds blow clockwise around a high pressure and diverge. Diverge, separate, diverge, outward, outward, and clockwise. This is the profile view. Sinking air, outward. This is surface winds blow counterclockwise around a low pressure and converge. They come together. Diverge, separate, converge, come together. Inward and counterclockwise. Lick. And here it is. Here's the profile view. Pulling inward, low suck, rising, and then you have a little cloud patch right there. That brings me to this. Pumpkins, pause this video, grab your reference table. Don't be intimidated. It looks scarier than it is. Okay, once you have this is on page 14 of your reference table. I'm going to explain it to you. Now, some of this got cut off, but whenever we start on a new chart in the reference table, we start at the top and sides and with the definition and the title of the chart. So this is called Planetary Winds and Moisture Belts in the Troposphere. I know it got cut off on here, but just read your reference table along with it. It says, the drawing on the right shows the locations of the belts near the time of an equinox. We just passed an equinox. That's the first day of spring. Locations shift somewhat with the changing latitude of the sun's vertical ray. In the northern hemisphere, the belts shift northward in the summer and southward in the winter. If that's Chinese to you, don't worry about it. I didn't teach you seasons yet. But this is not going to be Chinese to you. So grab your reference table and you look on with me at this chart. Now, it looks crazy. Don't fear. It's not as scary as it looks. Let's start at the beginning. First, you'll notice that there is a big, bold black line right here. That big, bold black line is Earth's surface. Okay, let me get this a little clearer for you. All right, this is Earth's surface. And so everywhere between that bold black line and this dotted line along the outermost edge, that is the tropopause. So think of the surface as being sea level. Just assume that it's sea level. And the dotted line is the edge of the troposphere. This is not drawn to scale. Remember, the atmosphere, the entire atmosphere, it's very, very thin. And it's not an accident that the atmosphere chart is on the same page as the planetary winds and moisture belts. That's because winds and weather are all right here in this skinny little layer known as the troposphere. So that dotted line is the tropopause, where the troposphere ends. Okay, and you'll notice that there are all these arrows going crazy all over the place. Don't worry about the arrows in the center for a second. Let's just look at the arrows at the edge. Start at the North Pole. Most people, when they think of the North Pole, they think storms all the time, it snows and ice all the time. That is not true. Because it is cold, the air is contracted. Because the air is contracted, moisture can't move in. And because the moisture can't move in, it stays very, very dry. That says dry. The poles, both of them, are deserts. They are polar deserts. Desert does not mean hot. Desert means dry. And the poles are super dry because they're so cold and contracted. So why is there ice up there? Well, even in deserts, hot deserts or cold deserts, it does actually precipitate. It just precipitates very infrequently. And in the case of the poles, when it does precipitate, it falls as ice and it just really doesn't melt. Now, of course, that's changing because global warming and all of our emissions and our pollution, that is changing. But let's just teach how things have happened for pretty much all of human existence, okay? It does snow at the poles, it just snows very infrequently, and when it falls, it just doesn't melt. So the ice at the poles, if you dig down through that ice, you're going into some very ancient snowfalls as you get deeper and deeper and deeper. But let's just say there was a snowfall this month. It's not gonna melt. And a snowfall last month, it's still there. And a snowfall 27 years ago, it's still there. That's why the poles are icy, even though it doesn't snow that frequently at the poles. That said, once you know that it's dry, you know sunny, high, cool, and dry. Sunny, high, cool, and dry. And high pressure drops. So if you look at this black line, that's the surface of the Earth. This is the tropopause. And so the air at the North Pole is dropping and spreading out. This is way up high in the atmosphere. This is the surface of the Earth. And if you follow these arrows, they're actually making circles. But at the poles, it is dropping and spreading out. High, outward, and clockwise. And where is it going? Well, away from the pole. Let's look at the equator. Doesn't matter which side, whichever side you're comfortable with. At the equator, the air is very warm, and warm air lets moisture in. And so if you look along the equator, it says wet. You might want to grab your pen, and next to that, write in parentheses, low. Low pressure. It's wet because it's low pressure. It's so warm at the equator that it allows lots of moisture in. And so this is where the rainforests are. It's wet. When people think of the tropics, they think, oh, it's so beautiful out all the time. That's true, except it rains every 2 hours. It's beautiful, then it downpours, then it's beautiful again, then it downpours, then it's beautiful again. It rains all the time in the tropics because it is warm. That makes it low pressure. And now if you go to the edge, either side, doesn't matter which side, if you go to the edge, think about it. Warm air wants to rise. Why? Because it's less dense. And as it rises, it condenses, it rains out at the equator, and then it drops to places away from the equator. Because now it's been up here, much higher in altitude, it got cooler, and that air wants to drop. It can't drop where there's this updraft. So it drops at other latitudes. What latitudes does it drop at? Well, it was rising at 0, and if you follow these arrows around, follow this arrow around, you'll notice that it lands you at these 2 planetary belts. Both of these 2 planetary belts say dry. Next to dry, you might want to grab your pen and write high, high and dry. Happy, high, cool, and dry. This is cooler than it is at the equator, and therefore it's dry. All the moisture rained out between these latitudes. And where did the air drop? Here, 30 degrees north, and here, 30 degrees south. Same thing here. Rose at the equator, rained out at the equator, and then dropped where it could, 30 degrees north and south. Kids, the world's deserts, the hot deserts, are at 30 degrees north and 30 degrees south. Check it out. The Sahara, the Mojave, many of the world's deserts are at 30 degrees north and south because these are very dry wind belts. Okay? And if you keep going, let's see where this cool air went to, right? The cool air at the poles. Let's go back to the poles for a sec. It drops and it spreads out. Now, let's go inside this circle. You'll notice that there are arrows on the inside of the circle, and they look a little crazy. They look like they're going all... They're really not. They are going in circles, just like the circles we drew. Just like this. This clockwise in the north, counterclockwise in the south. If you look at these arrows, just the ones between 30 and 60 degrees north, you'll notice that some of them are going this way and some of them are going that way, but if you follow this around, it's really making a circle. Right? If you follow any of these around, they're really kind of making circles in the north, circles in the south. So don't let these arrows intimidate you. They're not that scary. All right? If we go to the pole and I say, well, where are the winds coming from? If you look very, very closely, it says NE with arrows. NE stands for northeast. Where are the winds coming from? Well, remember that winds are named after where they come from. So here the winds are coming from the northeast, but if you look at that direction, that's the exact opposite of the northeast, right? The winds come from the northeast, but they go to the southwest. They go from the northeast to the southwest. Between 60 and 90 degrees north, that's where the winds are coming from. If I were to ask you, where are the winds coming from at, I don't know, 75 degrees north latitude? Here's 60 north. There's the pole, 90. 75 would be in between here. So they're coming from the northeast, blowing to the southwest. Let's think about New York. What is New York's latitude? Our part of New York is about 40 degrees, 30, maybe 40 minutes north. Let's call it 41 degrees north. Let's just say that we're 41 degrees north. 41 degrees north lives between 30 and 60, right? Here's 30 degrees north, here's 60. So if I ask you, what direction are our winds generally coming from overall, every day? Overall. Here it says SW winds. SW is southwest winds. And so the winds are coming from the southwest blowing to the northeast. From the southwest to the northeast. Where are they coming from? Southwest. Where are they blowing to? Northeast. Are you with me? See if you can do it. If I said I live at 15 degrees north. 15 degrees north of the equator. Here's 0. Here's 30. Where are the winds coming from? Well, in between 0 and 30 would have to be 15 degrees north. So, right in here it says NE winds. NE stands for northeast. Where are the winds coming from? They're coming from the northeast. Where are they going to? They're blowing to the southwest. From the northeast to the southwest. So the direction of the arrow is where it's blowing, but this is telling you where it's coming from. Winds are named after where they come from. Do 15 degrees south. 15 degrees south winds coming from the southeast, blowing to the northwest, and they converge. They converge. Are you with me? You could do that for any latitude. Now, let's put some things together. I want you to tell me anywhere where arrows come together. Anywhere on the globe where arrows come together, where they converge, will it be wet or dry? Let's start dead center. Here are arrows converging, coming together. They're coming together. And you don't only have to look in the center, you could look at the edges too. Along Earth's surface, here are arrows coming together, coming together, coming together, coming together. Is it wet or dry? It's wet. Let's find another place where arrows converge. Here, these arrows are moving apart. That's not converging. Here, arrows are moving apart. Let's go towards the North Pole. Here's an arrow, and they're kind of coming together. Over here, this arrow is moving this way, this arrow is moving this way. They are converging. Over here, converging. Anywhere you see arrows moving together, here and here, here, coming together, it says wet. Converging will make it wet. That is a low pressure area that is sucking the air in. Lows suck, right? Lows suck, it makes it wet. Look down here. Arrows converging, coming together, it's wet. 60 degrees north and south, it's wet. It's wet. Low pressure. Cloudy, low. Warmer, rain or snow. Warmer than the poles for sure. It's dry at the poles. And let's see why. Look at the arrows. Are the arrows converging or diverging at the poles? Diverging. Here, this is dropping. Remember that this is towards the surface over here. All right, it's clear at the North Pole. Just remember that. Down here is space, so this is dropping towards the surface. But it's it's diverging. Diverging, dry. Diverging, dry. Think about where the world's deserts are. 30 degrees north and south. Well, let's go to 30 north. Are they converging or diverging? Well, if I look at the edge, this arrow came down and spread. Down and spread. If this is harder for you to read, look here. Arrow going one way, arrow going the other. These are diverging, 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 and it's dry. Diverging, 30 south, diverging, diverging, dry. Anywhere the arrows converge, it's wet. Anywhere the arrows diverge, it's dry. So you got wet at the equator, warm, wet, rising air, cloudy, low, warmer, rain or snow. Sunny, high, cool, and dry. Cloudy, low, warmer, rain or snow. Sunny, high, cool, and dry. Okay? So this can be used with latitude, longitude. This can be used, they might ask you about altitude. What happens if air is rising? You know, is it going to be wet or dry? They could ask you about wind direction. It's all right here. Just make sure you go between the latitudes. Okay? That's how to use this chart. All right? Here is a diagram showing the same thing. This is the equator. This is the curve of the Earth, and this right here is the equator. So instead of looking at it straight up and down, they turned the Earth, so now you're looking at the equator here. Here, the air is rising, which makes it rain. It's converging. This arrow and this arrow converging, rises, cools, condenses, and makes it rain out, and then it drops back down at 30 degrees north and south. That makes it dry at these latitudes, wet at this latitude. Here's another diagram of the exact same phenomena. I know the arrows look crazy. Just remember, they're really making circles. They're not as crazy as they look. Clockwise in the north, counterclockwise in the south. They try to go in straight lines, but they deflect because the Earth is rotating. Wherever the air is warm, it's going to be low pressure, lousy weather, lots of rain. Wherever the air is dropping, 30 degrees north and south, it's going to be sunny, high, cool, and dry. All right? I just want to show you one other thing. See these little circles with X's? These are called jet streams. These are where the world's real powerful wind changes occur. Okay? The polar jet stream, this is basically the edge of the polar air. Same thing here, polar jet stream. And these are the tropical, subtropical jet streams. Subtropical, below the tropics. So past the tropics, right? And here the air is very dry. So these are the major wind belts. Major wind belts. The wet ones at 60 north and south, the dry ones at 30 north and south, and then of course the equator. That is pretty much it. Here's another one. I like this because it's color-coded. Red is warm, blue is cold. You'll notice at the equatorial low, nice and red, that makes it wet. At the poles, nice and blue, that's cold. Here they have an H, and H is where it is dry. The world's deserts, high pressure, sunny, high, cool and dry. Remember, desert means dry, not hot, all right? Now, I put up some videos, all right? I'm going to show you part of the first one. You can click it. But this is just the most beautiful video. It's put out by NASA. And this is back in 2006, and it goes through to, I think, 2007. Let me get this full screen. What I like about it is that they kind of piece together stuff from basically satellite views of particulates and other things in the atmosphere for the entire Earth's surface. And it shows carbon dioxide and pollution, but you could see the latitudes. And as it plays, you'll notice down here it says January 3rd, 2006. As this plays, it goes through the different years. It goes through the months of the year, and it goes through several months of observations. The red that you're going to see is carbon dioxide. But it's beautiful. You could see where the convergence is, where the divergence is. I strongly encourage you to play this video a couple of times to observe it really carefully. It's only 3 minutes. I'm going to show you some of it so that I can kind of walk you through it.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere.
All that red is carbon dioxide.
The visualization compresses 1 year of data into a few minutes.
So now we're February 5th, 6th, 7th, 8th.
Carbon
This is
dioxide
2006.
is the most important greenhouse gas affected by human activity.
This
About
is
half
us
the carbon
burning
dioxide
stuff.
emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean
Just look
reservoirs.
at how this air is coming together here
In the northern hemisphere,
and
we see
separating
the
here.
highest concentrations are focused around major emission sources over North America, Europe, and Asia.
That's North America, that's Europe, that's Asia. Here's
Notice
South
how the
America,
gas doesn't stay in one
here's
place.
Australia.
The dispersion of
This is carbon dioxide.
is controlled by the large-scale weather patterns within the global circulation.
Right? But look at how the wind is coming together at the equator and then separating out and going the other way.
During spring and summer
Now
in the
watch
northern
this.
hemisphere,
It's May.
plants absorb a substantial amount of carbon dioxide
Plants.
for photosynthesis, thus removing some of the gas from the atmosphere.
So look how red this is right
We see
before the
this
plants
change
come
in the
out.
model as the red and purple colors start to fade.
This was all of winter months and everything else, but now it's June. Look at how the plants just breathe all that carbon dioxide in. We got to get better about not emitting so much, but the plants just breathe it in and just truly clean the air. So plant some
Meanwhile,
trees,
In the
pumpkins.
southern hemisphere, we see the release of another pollutant carbon monoxide.
Monoxide.
This is a gas that's both harmful to the environment and to humans.
Because they're burning the trees down.
During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia.
This is fire.
Contributing to high concentrations in the atmosphere.
Coming together at the equator,
Notice
separating
how
out
these
here.
are also transported by winds to other parts of the world.
Okay, I'm going to pause this here. He goes on to talk about moisture in the atmosphere and other things. This is such a beautiful visualization. You could see where the winds are coming together, where they're separating out. You could see there's much more landmass in the northern hemisphere, and that's why those plants really take in the carbon dioxide. They really play a role in global air quality, and we do too, so we can do better. Okay. When you are finished viewing this video and maybe going through the slideshow, again, you can stop right here. This is slide number 35. Everything that comes after this will be at a later lesson. Okay? Okay, I hope this helps. If you have any questions on page 14 of your reference table, or wind, or Coriolis effect, or, anything, hit me up. All right, go do your castle learning, and I will shoot another video probably Monday or Tuesday, and we'll talk. Have a great weekend. Enjoy your holiday.